Okay, so now we're going to talk about the molecular geometry. So as you know that molecules are a three-dimensional structure, right? Because in nature everything is a three-dimensional molecule, right? And if it's a three-dimensional molecule, then you should have some corners, right? So each corner represents each atom. Let's say if this is your room, and at the center of the room you have one atom, and all the four corners of the room you have one atom, right? So this is how the three-dimensional structure looks like. Right? And then if you have a three-dimensional structure, then you should have some bond angle, right? We'll see what is bond angle, as the name is saying, the angle between the bond. So there are three geometrical figure that you need to know depending on how many atoms they are making it. Three, so one of them is linear, second is trigonal planar, third is tetrahedral. So when you make a linear molecule, when you have three atoms, one at the center, two surrounding it, right, on each side of the central atom. And then what is bond angle? Bond angle is the angle between two consecutive bonds. So this is 180. Trigonal planar, how many atoms you need for trigonal planar? You need total of 4 atoms, one at the center, three surrounding it. And the angle between two consecutive bond or two alternate bond is 120. So this is also 120, right? This is also 120. So this is trigonal planar. Tetrahedral should have 5 atoms, one at the center and 4 surrounding it. 1, 2, 3, 4. And the angle between the two consecutive bond is 109.5. So you have to remember this angle and the name of the geometrical figure, right? Which one is tetrahedral, which one is trigonal planar, which one is linear, right? I might ask you in the exam and quiz the angle and the name. Okay, so now the question is why you have, if you have three atoms, one at the center, two surrounding it, why always the structure looks like linear? Why I cannot make the structure something like this? Something angled. Why is always a straight line, right? Why if you have four atoms, one at the center, it's like a triangle? Why it cannot be like this? Right, all the three atoms at the same side. So there's some reason why you have the structure like it's showing you over here, and it's because of one of the theory that we're going to discuss right now. That theory is known as VSEPR theory. So what's the VSEPR theory? This is a short form of valence shell electron pair repulsion theory, as the name is indicating. Valence shell electron pair repulsion means, in this theory, they say if you have two bonds together, two bonds cannot be together because of the repulsion between the electron. So if you go in the previous slide over here, so you have two bonds, you have a one bond, you have two electron, right? Between, you have two electron. So this is the perfect arrangement of the two bond so that the electron cannot repel each other, right? You cannot have two bonds side by side because they will repel each other, because electron and electron repel each other, both are negative charge. So the atom has to arrange, the structure has to be arranged such a way that the bonds should be as far as possible so that the electron in the bond cannot repel each other. If it's a repulsion, is the minimalistic repulsion, right? So if you have less repulsion means more stable. Similarly for trigonal planar, why the structure is look like a triangle? Because this is the perfect arrangement of bond so that they will reduce the repulsion between the two bonds or the two electrons, right? So this is the perfect structure. For tetrahedral, this is like a pyramid. If you have seen the pyramid, right, it's something like this, right? So this is the perfect structure for tetrahedral, if you have 5 atoms, one center, 4 surrounding it, the angle between the two bonds should be 109. If you have less than that, more than that, there will be high instability, right, because of the repulsion. So that's how, so that's VSPR theory normally tells about, right? This is all about the VSEPR theory, right? So again, is the same thing, linear, right? Right, like I said, you can read it along it with the same thing that I explained. Trigonal planar, right? You have the perfect structure so that there will be less repulsion. Similarly, tetrahedral, right? Okay, so now we already learned about the three structure, most basic structure, but sometimes they are different shape beside linear, triangular, planar, and tetrahedral. There are some other shape that you need to know why there are other shape beside this one, right? Okay, so let me ask you, let's say if I give you one example, let's say you have water, H2O, the simple molecular structure, right? Molecular formula of water. So if you draw the structure using the same loose structure theory, right, like I explained, oxygen at the center, find the total number of valence electron, everything, you will see the structure by yourself, right? So how many atoms you have in this water? You have 3 atoms, 2 hydrogen, 1 at the center. What should the structure you think of? It should be linear, right? If you have 3 atoms, 1 at the center, through 2 surrounding it, it should be a linear structure that we learn. But if you draw the loose structure with the same concept that I explained how to draw the structure, you will see you left with 2 lone pair on the oxygen atom, right? This is the loose structure. But what happens when you have a lone pair? If you have a lone pair, this is close to this bond, and they have very high repulsion between the lone pair and bond pair. So because of this lone pair on the central atom, what's happened? It repel the bond a little bit down, right? So the bond will bend down so that there won't be any more repulsion, right? So so before the repulsion happened, what should be the structure? 180. But because of the repulsion, the bond moves down. Now the angle is less than 180, less than 180, right? So always remember this thing, whenever you have a lone pair, doesn't matter how many, one lone pair, two lone pair, three lone pair. If you have a lone pair on the central atom, only on the central atom, remember this thing, mark this thing, not on the corner atom. In this case, you don't have, but there are some instances that you might have some lone pair on the corner atom, but it doesn't matter. The only thing matter is you have to have some lone pair on the central atom. That's how you normally show a derivative structure. So we normally tell this type of structure as bent structure because it got bent, right? So yeah, so remember, only on the central atom you have to have a lone pair. If you don't have a lone pair on the central atom, the structure will be one of those three structures that we learn: linear, tetrahedral, or diagonal planar, right? So yeah, so keep this in mind. Okay, so now let's get back to the slide. I think we have some example. Let's take, if I have some example, we have one example. So this is one of the example. If you see SO2 molecule, right? So you have one center, two surrounding it. It should be linear, but why is not linear? Because of this lone pair on the central atom. It doesn't matter if you have a lone pair over here or not, but you have a central lone pair on the central atom, and because of this, it will get bent down. You will see over here. This is your sulfur. This is your oxygen, right? So the structure will be bent. It's not linear. So I might give you in the quiz what's the structure of SO2 molecule. You have to pick a band shape, not the linear one. yeah, we have many example given on the PowerPoint, right? NS3, ammonia. The structure will be a band structure because you have a lone pair on the nitrogen. Water, I already told you, is a band structure because of lone pair, right? So yeah, this thing you have to remember. Okay, so now let's try to do some example, right? I'll give you one example and then you have to do all of the example by yourself, right? Let's talk about the first one, ClO2. So we already gave you the structure. You don't need to draw the structure because this exercise just to tell us that whether the structure will be linear, not triangular, planar, tetrahedral, or bent. So if we talk about this structure, what do you think the structure will be? You have one center, two surrounding it. It should be linear? No. Why? Because you have a lone pair on the central atom. Because of this, it get bent down. So the structure will be something like this. ClO, right? So this is the same lone pair over here. 6 and 6 on this, right? So the shape is will be bent. Let me write over here, bent shape, right? So yeah. So let me ask you about this S3PO4. What do you think the shape of the this molecule? So you have to see the center atom, which is P. How many atom you have attached to the center atom? 4. 1, 2, 3, 4. So if you have one center atom, 4 surrounding it, what should be the structure? Tetrahedral? Yes. So it should be a tetrahedral or a bent. It should be a tetrahedral. Why? Because on phosphorus, you don't have any lone pair. So the structure will be as usual, tetrahedral, right? You don't have any lone pair. So try to understand and answer all the remaining of the molecule by yourself, and then that will help you. The answer is already provided to you over here. So answer is already provided, even though it says TTR for the first example, tetrahedral band. So you won't, don't worry about it. If you just write band in your exam or quiz, you won't see tetrahedral band. You will see one option, just band. So you have to go for band if you think the structure is other than the three structure that we just discussed: linear, right? Linear, tetrahedral, and trigonal planar. Okay, so we finished with the structure, the Lewis structure and the shape. Now let's talk about the polarity of the bond. What is bond polarity? So bonding between the unlike atom result in unequal sharing of electron. Means, let's say if you have a two atom, you have a bond between them. Let me write over here. Let's say if you have A bond with B, over here. If you have bond with B, so you have electron, right? But sometime let's say B is stronger than A. What's gonna happen? It tells A that okay, I am stronger than you. This electron that you are sharing with me, I'll take a much bigger share of this. Means this electron goes close to this a little bit over here. Now the structure looks like this. The electron goes close to the B because B is more stronger, right? But even though it's stronger, A still have some part associate this, or you can say A still have some hold on it, right? On this electron, it's not transferring of electron. But what happen if this A electron goes close to the B? You will get some partial positive charge on it, and B will get partial negative. So if you see, I wrote plus and negative, but in plus in front of plus I use a special symbol called delta. This is called delta sign, and it's normally to show or tells partial. It tells you about the whatever the charge you have is a little bit partial. It's not complete positive or negative, right? Because there is no complete transfer. That's why, right? But the time you write, you can write positive, delta negative means what you're writing. You are making the bond as polar, because what do you mean by the polar? Like on Earth, we have polarity, right? South pole and North pole, right? Similarly, within the bond, we can say this bond is polar bond. And you will always get a polar bond whenever one of the atom is stronger than the other atom. That's how you normally get the polar bond. If both the atoms are same, no one is stronger than the other, then let's say C and D. In this case, C and D are both are same in the strength wise. Both, none of them are stronger with each other, right? So that means electron are shared equally, right? No one can snatch each other electron. So this kind of bond we call as, and then one, if we cannot snatch or if one cannot pull the electron a little bit close to each other, then we cannot assign positive and negative. We cannot assign. And once we cannot assign the partial positive, partial negative, we say that kind of bond as non-polar bond, because we cannot assign plus and negative, right? That's the main thing. Non-polar bond, right? Yeah, just bear with my handwriting, right? It's a little bit hard to write, but it says non-polar, right? Okay, so now the question is, how would you determine whether two element out of the two atoms, which one is stronger if there is, if not, how would you determine? So to determine which atoms are strong compared to the other one, there's a special term called electronegativity. So let's go to the slide and then that will help you to see. So we only talk about the bond. So like I said, how would you decide which atom is much stronger? So you can assign the which atom is stronger through the process or the concept of electronegativity. So electronegativity is the measure of the pull an atom has on bonding electron, right? So how much pull an atom can exert on the bonding electron. And then you need to remember this thing. Electronegativity increases across the period. Means if you go across the period, let me go on this side. If you go across the period, if you the electronegativity increases. If you go down the group, it decreases. On the slide is showing the arrow shown upward, means if you go up the group, it increases, right? And if you see, this is a copy of the periodic table, but instead of if instead of writing the name of the element in here, you are seeing some numbers, right? 2.1, 1.0, 1.5. What this number? This is called electronegative numbers. Bigger the number, more stronger is the element is, right? So if you see, if you will compare your periodic table side by side, so this 2.1 number belongs to hydrogen, because this is the space belong to the hydrogen element, right? This 1.0 is for lithium Li, right? So you can see the box and then compare with your periodic table, you will get the electronegative number for that particular element. So like I said, bigger the number, more stronger is the element, right? So and then once you get which atoms are stronger, then let's see if we have some example over here. So let's go over here. Then from the electronegativity number, we can decide whether the bond is polar or non-polar, right? Like I said, you have to have the number, right? Which atom is stronger. So just right now, write it down this scale. Then I'll explain you what this scale mean. How can we use this electronegative numbers to determine whether the bond are polar or not, right? So if you see this scale goes from 0 to 4. If the numbers come out between 0 and zero point 0.4, that means the bond is pure covalent. Means the sharing of electron is perfect. No, none of the element is snatching the electron or pulling the electron. They are both same stronger. If the number come out between 0.4 and 2.0, that means one of the element is stronger, a little bit stronger compared to the other one. That's why you can assign some positive and negative charge. But if the number come out between 2.0 and 4.0, that means the other atoms are so strong or is so strong, it there is no way the electron are in sharing. They directly snatch the electron, right? They say, okay, I'm so strong, I'm just taking completely, right, your electron from your orbit, right? We cannot share, I'm just taking it. So that's why you have ionic, right? Ionic is transferring of electron. You just transfer completely. Okay. So now let's see how we can use this scale. So let's take an example. I think we already have an example over here with chlorine and chlorine, right? This is one chlorine atom. You have second chlorine atom. If you make a bond, right, by single bond means you have sharing one electron from both sides. Then you have to see which element are stronger. How would you know? You have to go to the electronegativity table that I showed you, right, with the numbers. If you see that periodic table, you will see for chlorine, the number is 3.0. The other atom is also chlorine. That means the number won't change. Again, 3.0. So 3.0 negative 3.0. The final answer is 0. So where you have 0 in this scale? Here. That means the bond is pure covalent. Means the sharing is equal. There's no strong element, no weaker element, right? But let's say another example, HF, hydrogen fluoride, right? So hydrogen is here, fluorine is here. You have a bond between hydrogen and fluorine. If you if you remember, I told for hydrogen was the number on the electronegative table, 2.1. For fluorine, if you compare, you will get from the table 4.0 number. If you subtract both of them, you will get 1.9. And then you have to pick the scale where you have 1.9, somewhere here, 1.9. So that means the bond between H and F is polar covalent. So I can write H, F. Then hydrogen has electronegativity of 2.1. Fluorine has 4.0. So the time I write electronegativity, what do you think? Which element or which atom is negative, which atom is positive between hydrogen and fluorine? Bigger the number, more stronger is the atom. So this is negative partial. This is partial positive. Smaller the number, right? Because electron will go a little bit close to fluorine. Right? So so this is a polar covalent bond. Why is polar bond? Because you can assign positive and negative sign. Right? And the last one is ionic compound NaCl. So if you see, Na will have 0.9, chlorine will have 3. If you subtract, you will get 2.1. 2.1 will be somewhere in here. So it's come under ionic. Ionic means complete transfer. Sodium will completely transfer the electron to chlorine. Right? This is an ionic compound. Right? So remember this thing. Your subtraction cannot come out to be negative. Right? Just always subtract smaller number from the bigger number. Doesn't matter how the element form. In this case, hydrogen first, fluorine second. But you always subtract the bigger number for high fluorine from smaller number. Right? And then you will get a positive number, and then you can compare. right? Make sure you understand this concept, because you need to do one exercise in your lab that you have to write it down whether the bond in that lab is polar or non-polar, right? So make sure you know this thing. If you have still have doubt, you can come and ask me the question. Okay. Okay. Then you have one more topic called dipole moment. So dipole moment is nothing. It just tells you or measure the size of the polarity. How big is the polarity, right? You're just writing positive and negative across the bond, but you have to tell how much is the bond polarity means, right? Some has less polarity, some have high polarity, right? So you have to just know the definition is measure the size of the polarity. And the important thing that you need to remember, the dipole moment has a directionality, means you will always show a dipole moment from goes from positive to negative. This is important. So dipole moment always go from positive to negative. So you will always show with an arrow for dipole moment, right? So this is important. Okay. Then think we have to. So there's some example. Let's do one example over here. So from each of the bond molecule, PbO, PS, you have a bond. You have to tell me whether the bond is polar, non-polar, ionic, right? How would you do? You have to first go through the electronegativity table, assign the electronegative number for Pb and O, then subtract both of them, and then you will get some number, and that you have to use that number and compare with the scale. Then you can get the answer whether the bond is polar, non-polar, or ionic. So answer is already here, right? PB is 3.5 minus 1.9, you will get 1.6. This polar covalent if you compare this number, right? So this is how you normally do. Okay, now let's go to our last topic, which is polarity of molecule. So till now we just got the polarity of the bond, single bond, but what if I ask you whether the entire molecule is polar or not, right? So let me give you one example over here. Let's say for carbon dioxide, this is a gas. If I ask you this carbon dioxide molecule is a polar molecule or non-polar molecule, polar or non-polar, how would you determine? I'm talking about the entire molecule, not the bond, right? That you can get from the electronegativity table, right? So that's the difference. So to determine whether the molecule is polar or non-polar, you have to satisfy two conditions, right? In the same order that I'm writing right now. First, the bond has to be polar, or you can write polar bond. Right over here. So the first condition is you have to have polar bond. Polar bond. Second condition, you have to have a net. This term is important. Net dipole moment. You have to satisfy both these conditions before you can say the molecule is polar or non-polar, and you have to go through this sequence. If you find it out the bond is non-polar, for example, that means the molecule is non-polar, right? If you go from top to bottom, if you doesn't satisfy the first condition, means you don't need to go to the second condition because you didn't cross the first condition, right? So you have to cross each condition. First bond has to be polar, second net dipole moment, right? Okay, so let's try to do some example using the same two condition, and then that will be it for this chapter, I think. Okay, let's share the slide again. And then that will help you in the lab too, right? So understand. Good. Okay. So before we go to the do one example, let me explain you some small topic that might be helpful for you to solve the problem. So like I said, for carbon dioxide, this is a carbon dioxide molecule CO2. If you if you have to make, I think you can easily make this carbon dioxide molecule using the same concept that I explained. So I don't think any problem. So you will see something like this: C double bond O, double bond O. This is your carbon dioxide molecule, and then you have two lone pair on this, two lone pair on this. So this is a loose structure for carbon dioxide. Even though it's not showing, it should have something like this, right? But the main thing is that whether first you have to find whether the bond is polar or not, right? So if you see the electronegativity table, you will see this oxygen will have a bigger number, right? It can be 3, 4, or 2.5, right? You have to see. And then carbon will have a smaller number for electronegativity. So that means if oxygen has a bigger number, it will get, let me write with a different, it will get some partial negative charge because of this big number electronegativity. This will also get a partial negative charge, and carbon will get a positive charge because it has low or lower electronegative number, right? Or is less stronger. So if you remember both condition, first is bond has to be polar. You can do it easily by subtracting the number and then compare with the scale, then, right? The second is dipole moment. How would you know the dipole moment? You have a dipole moment. So for this thing, if you remember, dipole moment always go from positive to negative. So center carbon is positive, both sides are negative. So one of the dipole moment go this way, another dipole moment is going this way. So what do you think? This molecule has some dipole moment. If we assume bond is polar, let's assume bond is polar. We cross the first condition. Now we are on the second condition, right? We are assuming. So what do you think? This molecule has a dipole moment? Yes or no? So even though it has individual dipole moment, one dipole moment going on this direction, another going this direction, but what about the net dipole moment? The final, it has zero dipole moment. So this entire molecule doesn't have a dipole moment, net dipole moment. Why? Why I'm saying this thing even though you are seeing a dipole moment going on both direction? The thing I'm saying, even though they have both two dipole moment, but they're going equal and in opposite direction. So that means they're gonna cancel it out each other. And the net result will be zero. So you have to learn this small or the important thing. Even though the molecule has individual dipole moment, but you have to have some net dipole moment, right? So net dipole moment cannot be zero. If it's zero, then the molecule is non-polar. If the net dipole moment is not a zero, then the molecule is polar. So you have to understand this thing. Polar dipole moment doesn't make the molecule polar. Only the net dipole moment does. So make sure this is an important thing, very important, because some students just see, okay, this is a dipole moment, molecule is polar. No, because they might cancel it out each other, right? So this is important. So we'll see some example, right? Let's take an example for water over here, and then think. So this is the structure of water, right? We assume the bond are polar, right? We cross the first condition. And if you see from the electronegative number, oxygen has a bigger number. This is negative charge. Hydrogen is positive charge, has a small electronegativity number. So I'm writing positive. And if you know, dipole moment always go from positive to negative, right? So what do you think? Even though we have two dipole moment, right? But what do you think? They both gonna cancel it out each other or not? If they can cancel it out each other, molecule is non-polar. If not, then the molecule is polar. So if you see, both dipole moment is going in same direction. So there is no way they're gonna cancel it out each other, right? So we don't need some number. We have to just see whether they can cancel it out each other or no. They cannot in this water molecule H2O. So that means the water is polar molecule because you have some dipole moment, right? So this is the second. Let's do one. So this is a picture. This is very important for you. If you can understand this pictures or figures, then I think it's good. It's good for you to understand the dipole moment. So let's try to understand. If two dipole moment is going opposite direction, we know this is non-polar because they can cancel it out each other, right? If they are going almost in the same direction, upward, they are polar. There is no way they can cancel it out each other, right? Now this is the question over here. Now one of the dipole moment is going up, second is going over here, third is going here. Why you are saying this is a non-polar bond, non-polar molecule? So one is going, so let me show you this way. Okay, so let's understand the bottom one. If one dipole moment going this way, second going this way, what's the net result? Net result will be this way, right? If one friend wants to go this way, another friend wants to go this way, what's the final solution? Both the friends say, okay, we won't go in each other direction, let's go the center direction, right? Because we are going in the same direction, so don't follow, let's go the center. But the time you put the arrow in the downward direction, what you have over here, you already have equal and opposite force on the upward direction, means they can cancel it out. So you have a net dipole moment of 0. So that's why instead, even though you have 3 dipole moment going on in this structure, the ultimate net dipole moment is 0. Same happen for this. This is a tetrahedral, one center, 4 surrounding atom. So the thing is that you need to remember, if the molecule is symmetrical, means linear, trigonal planar, this is trigonal planar, if you remember, right? One center, 2 surrounding. This is tetrahedral, one center, 4. So linear, long, linear, trigonal, planar, tetrahedral, all these are symmetrical molecule. So for symmetrical molecule, the net dipole moment will always be 0. You can say that, right? So that means the molecule will be non-polar, right? But for an asymmetrical molecule, like something like for a band shape, like water, for asymmetrical molecule that doesn't have a symmetry, there will always be some dipole moment. Means the molecule will always be polar. If you satisfy the first condition, then you will always have a dipole moment, right? For the unsymmetrical molecule. Right? Let's take one last example and then we'll finish this chapter. Right? You have to tell me whether NH3 ammonia is a polar molecule or not non-polar molecule. So your first step will be draw the structure. If you don't have a structure, how would you assign a dipole moment, right? In which direction? So first you have to draw the structure, and I hope everyone know how to draw the structure, the same concept, right? Total number of valence electron, everything. So everything is solved. The structure will be over here. This is your structure. But what do you think? This is the right structure? No, because you have a lone pair on the central atom. The structure cannot be like this. These two bond has to go down, right? Like in this case, this one goes down, right? It's a band structure because of this lone pair. So once you know the structure, second thing is to find whether the bonds are polar. And first thing is where to find whether the bonds are polar and non-polar. This is the first condition before we can say molecule is polar or non-polar. Okay. So if you see the electronegativity number, you will find it out the bonds will be a polar molecule, right? Because nitrogen has a bigger electronegative number and hydrogen is a less electronegative number. If you subtract, you will get some number that you need to compare with the scale, like we already did, right? And then once you figure it out the bonds are polar, second condition is to figure it out whether you have a dipole moment or not. So if nitrogen has a bigger electronegative number, you will get a negative charge. Each hydrogen will get a positive charge. And you know dipole moment goes from positive to negative. So if you see, each dipole moment is going upward. So there is no way that these dipole moments gonna cancel it out each other, right? Because the structure of this ammonia will be a band structure. And now because of band, this structure will become asymmetrical, right? So you have a polar bond. First condition met. Second condition is there is a dipole moment. Yes, there is a dipole moment in this ammonia because everything is going up. There is no way they can cancel it out. So you have a net dipole moment. Then we can say the molecule ammonia is a polar molecule. You can say it, right? So molecule is polar if you can see over here. Similarly, you can try this example. So you have to do it by yourself. This example, this NOCl and SO3. This is the electronegative number already given. So let me explain this last example for you, right? And then you can do the SO2. So the time I see the lone pair on the central atom, I know the structure will be something a band structure, right? Right. This is the structure, band structure, and you have a lone pair on the top. So now the first thing is to figure it out bonds are polar or not. So how would you do that? Nitrogen has an electronegative number of 3. Oxygen has 3.5. So what's the difference? This is 3.5. This is 3.0. Chlorine has 3.0. 3.0. So if you subtract to figure it out how many bonds you have 2 bonds, one between nitrogen oxygen, one between nitrogen chlorine. So nitrogen oxygen has the electron number 3.0 and 3.5. Was the difference? 0.5. Now you have to see where this 0.5 belongs in the scale. This is a polar bond if you met. Now let's see over here 3.0, 3.0. So 3.0 minus 3.0, you will get your answer as 0. You have to see where the 0 is belongs in the scale. So this is a non-polar, right? So what we figure it out from here? We figure it out. No. We figure it out from here. Let me remove this one. We have a, let me, so this is a bond, right? So what we figured out, this bond is non-polar, right? But this bond is polar. So if you can see, there's a special thing in here. Within the same molecule, one of the bond is non-polar and the second bond is polar. So you can still find it out whether the molecule is polar or non-polar, even though you have one of the bond is non-polar, right? So to make the molecule polar, you need just one polar bond. Doesn't matter you have 100 of non-polar bond, but if you still have one polar bond within the same molecule, still there is a chance that the molecule can become polar, right? So if this is a non-polar bond, we cannot assign positive and negative charge in between these. And if I cannot assign positive and negative charge, I cannot assign a dipole moment, right? Dipole moment always go from positive to negative. So we're not concerned about this structure anymore, right? Now let's focus on just this thing. This is a polar bond, right? So nitrogen has 3.0, 3.5. This should be a negative charge, bigger electronegative number. 3.0 is a positive charge. So which way the dipole moment will go? From positive to negative, right? Dipole moment, right? dm. So you have a dipole moment, you have a polar bond. Is there any, this dipole moment is going to cancel it out? No, because there is no other dipole moment. You have just one. So you met both the condition. Bond is polar, doesn't matter if you have just one bond polar, but you met this condition. Second condition that you met is you have a dipole moment, net dipole moment, right? So that means this molecule is polar molecule, right? So yeah, so this is how you normally do the problem. The answer is already provided in the last slide, right, that I explained, and you already have the answer for the second structure, but make sure you try it by yourself first and then see the answer if you stuck somewhere else. And so yeah, so that will be it from this chapter. So we already covered everything that might not, that will be helpful for your lab too, right, whenever you do the lab. So yeah, so if you have any question, try to come to my office hours and then we'll do over there, right? So yeah, I'll see you in office hours if you have any question, right? Have a good day. Bye.